Hello, welcome back to Larry's Classroom. Today we will continue our discussion of circuits that have both series and parallel parts to them. And like usual, we're going to begin with a drawing and we're going to talk about it a bit. So we're going to draw a circuit up here and we're going to have a resistor, another resistor, we're going to supply this with a 200 volt supply. We're going to call this guy R1, and that's going to be a 30 ohm resistor. R2, 8 ohm, 8 ohm resistor. R3 right here, and that's going to be a that's a 24 ohm resistor. R4, that's going to be another 24 ohm resistor. Another resistor here that we missed. That's R6 at 60 ohms. So we got a R1 right here. Where's R1? Okay, there's R1. R1, R2, R3, R4, R5. And that is a 20 ohm resistor. First thing we're going to do is look at this and identify the series elements. Well, current full flow through here is split into these two branches, come back to here. So basically R1 and R6 are in series with the network created by R2, R3, R4, and R5. Now let's look at what we have for parallels portions. Well, right here R3 and R4 form a parallel circuit, which we will find the equivalent resistor. We'll replace that with a single resistor. Then we will have R2 and this network in series, and then we'll find that this branch and this branch are in parallel. We'll reduce them to a single network and we'll end up with a 3 resistor in series type network. So we're going to start by looking at this small little R3, R4 parallel branch. Well, you notice that these are 24 ohm resistors. And we've talked about parallel resistors when they're equal value. We can use this formula that says R equivalent is equal to R divided by N, with N being the number of branches. So we have here 2 branches, 2 equal value resistors. So what we end up with here is that R equivalent is going to be the 24 ohms divided by 2, which will be 12 ohms. So we can replace this with a 12 ohm resistor. So we're going to do a quick little sketch of that piece over here. We're going to go ahead and put R5 there, which is 20 ohms. And we're going to leave R2, we're going to draw it around the corner of the drawing, which would be R2 equals 8 ohms. And then we're going to make a single resistor to replace this. So if we have the single resistor, we're going to call that R34. R3-4, and we used the formula. We said that 24 divided by 2 is 12 ohms, so that has an equivalent resistance of 12 ohms. Now, we see here that 12 and 8 is 20, so this little piece here is going to look like two 20 ohm resistors in parallel. 20 ohm, 20 ohm. Well, we know from using this formula that we can do that again. 20 divided by 2, replace that whole thing with a 10 ohm resistor. So what I'm going to do now is I'm going to redraw this circuit, replacing this entire piece with a single 10 ohm resistor. We first found a parallel combination for this, which we said was 12 ohms. And we use this formula here, R divided by N, to find the value of it. Then we added the 8 and 12 to get 20. We added the 20 ohm. The 20 ohm didn't change, but then we used this again to get R divided by N to get 10. So what we've determined is that this entire piece here that I'm kind of dotting out in red can be replaced by that single 10 ohm resistor. So we're going to kind of do that. So we're going to draw another little circuit here. And we're going to leave R1 here, which is a 30 ohm resistor. We're going to put the 10 ohm resistor that we used to replace this entire thing, this entire portion circled in red. And we're going to leave the 60 ohm. I'm going to put some polarities on that. We still have the 200 volt power supply. Make this a little bit nicer to look at. Now we can, using our series total resistance formula, we can add these three resistors up and count with a single resistor. Well, 30 plus 10 is 40, plus 60, 100 ohms. So we can replace this whole thing, this entire network that we have up here. So we have 200 volts, we have 100 ohms. Now the object of doing that, reducing this network to a single resistor, it makes it very easy for us to find the total current, which we have seen many times that our current equals voltage divided by resistance. What do we have here? We have 200 volts. And I'm going to put it on the side here. I'm not going to put it right inside there. We have 200 volts supplied divided by 100 ohms, which gave us 2 amps. 200 by 100, 2 amps. So we're going to draw a little 2 amp arrow here, showing that we have 2 amps going around through that series circuit. We've reduced this series parallel circuit down to a single resistor. Well, this is the same circuit, so we're going to put the 2 amps here as well. Now we're going to utilize another formula we've used quite a bit, part of Ohm's law of voltage. Another form of Ohm's law of voltage equals I times R. Current times resistance. We have 2 amps, and we're going to calculate voltages across each of these 3 pieces. Well, 2 amps times 30 ohms, that gives us 60 volts here. 2 amps times 100 ohms, that gives us 20 volts here. 2 amps times 60 ohms, that gives us 120 volts. Did I do that right? 60, 30, 60, 80, 60 volts. $20 volts. Oh, okay. This is 60 ohm resistors. 120. Okay, 120 volts. Yeah, 120 volts. 120 volts plus 20 volts plus 60 volts. Yeah, I was looking at the ohms here. 120 plus 20 is 140 plus 60 is 200 volts. So we find that our voltage summation formula, that the voltage applied does equal to the voltage drops, which are right here. Now this 60 ohm resistor, or this 30 ohm resistor with 60 volts across, never changed, so we're going to go ahead and add that, call it V1 equal to 60 volts. And this 60 ohm resistor we didn't do anything with it either. So we're going to put the V6 equal to 120 volts. Now we're going to add another little spot, another little bit of information here. We're going to put a little arrow in here. And this network here is represented by the 10 ohm resistor. It has 20 volts across it. So we're going to put 20 volts right here. And that will be the applied voltage, or the resultant voltage from the applied voltage after these voltage drops that is across this network. And if you take 200 minus 60, you get 140 minus the 120. That gets you down to the 20 volts we have here. So still our 60 plus 20 plus 120 adds up to 200. Now, this 20 volts across this network allows us to do a couple things. First of all, we calculated our total 2 amps. So let's put that up here. Let's move it up from here. 2 amps in this direction. So we have 20 volts, and that's across this branch and this branch because they're parallel. Let's figure out the current in R5. We'll call that I5. We'll use the I equals V over R, so I5 equals 20 volts divided by 20 ohms. We got 1 amp, don't we? 20 volts. Divided by 20 ohms, 1 amp. So let's go ahead and put 1 amp right here. So we have 2 amps coming into this main line of this series and parallel combination network of resistors. We've calculated that through this branch, which we call as I5, branch 5, we have 1 amp of current. Well, you remember our current summation formula. The 2 amps here minus the 1 amp here also leaves 1 amp here. So we have 1 amp flowing through that half and 1 amp flowing through here. Now, what does this allow us to do? We have found the currents everywhere but these 2 resistors. But this branch has 1 amp, this branch has 1 amp. We calculated total resistance to find total current. I'm going to call that IT, by the way. I total. We have 2 amps flowing in. We have 1 amp in this branch, 1 amp in that branch. We use the summation of currents type calculations. But now that we know the current through the 8 ohm resistor, we got one more formula. We've used this one quite a bit. Voltage equals I times R. 1 amp times 8 ohms, that's 8. So we end up with 8 volts here. So that gives us one more piece of information about this circuit. Now we know there are 20 volts across the entire thing. I'm going to erase some of this. I don't think we're going to need this anymore. We use that to find the total current. But we know we have 20 volts across this branch, and VT equals V1 plus V2. Well, we're going to call this V1 and this V2. It's really the voltage across here to be V2. What we're trying to find is the voltage across this network. We had 20 volts from here to here. That equals the 8 volts here plus whatever's there, which I'm calling V2. Subtract 8 from both sides, we end up with 12 volts equals V2. By using the voltage summation formula, we found that there are 12 volts from here to here. Let's put it right in there. Now, this enables us to find the current through R3 and R4. Well, R3 and R4 both have 12 volts across them, dropped. And we got the formula here, voltage equals I times R, current times resistance. That's what we want to use. We're wanting the current for. Current equals voltage divided by resistance. Well, V3, VR3, let's call it VR3. V across R3 will be equal to 12 volts divided by the value of R3, which is 24 ohms. That's basically 1/2 amp. Now we could do the same calculation for R4, but we have the same voltage and the same resistance, so it's going to be the same. It will be the same current. So I'm going to put 1/2 amp here and an arrow pointing that way. I put 1/2 amp here and an arrow pointing that way. So we calculated the equivalent resistance, the total resistance. From that we were able to calculate the total current. Total current we were able to compute voltage drops. That allowed us to compute the current through R5, and because of the summation of currents, it allowed the current to us to know the IT minus the current through R5 gave us the current through this branch. So now we need the current everywhere but these two. Using our current equal voltage times resistance, or voltage divided by resistance, we're able to calculate the current here. What you also will notice is that they're identical resistors, so we could have just said divide this current by 2. So 2 amps comes in, splits 1 amp through here, 1 amp there. The 1 amp comes into here, splits 1/2 amp through here, 1/2 amp through there. Well, then it comes out and recombines into 1 amp. And when it passes this point, the current through R5 and the current through this side of the branch combine again to give us 2 amps, just like we initially had. So got the arrow the wrong direction. So the current returning to the source is the same as the current that left. The current into this network, which was a total of 2 amps, split up, recombined, same amount come out. We had 1 amp go into R5, and we had 1 amp come out of R5. We had 1 amp come out of this network, we had 1 amp come out of this network. We had 1 amp come into here, split into 2, recombine back into 1. So we've got all our currents are adding up. We've calculated the voltages here, the voltages here, the voltages here. Well, we calculated every voltage. We have 60 volts, 30 ohms, 2 amps. 8 volts, 1 amp, 8 ohms. 12 volts, 24 ohms, a half an amp. 12 volts, 24 ohms, a half an amp. 20 volts, 20 ohms, 1 amp. And we had 1 amp times 60 volts to get 120 volts. We've calculated all voltages and all currents in this circuit. And we did it by combining these parallel resistors into a single resistor, then combine the series resistors into a single resistor, and then we had another parallel combination that we combined into a single resistor, which got us to here. Then we combined this series of resistors into a single resistor. So we had to find RT with this type of a circuit, and that allowed us to work our way back and solve everything in the circuit pretty much. So we're going to erase that. We're going to look at a little bit more about analyzing series and parallel circuits. We're getting some practice. I think that you'll probably be able to follow what we're going to talk about. So we're going to start out with some rules related to analyzing series and parallel circuits. Rules to help us think about what to do. So the first one is, with parallel strings, strings across the main line, across a main line, we can find IT can be found without finding RT. So what does that mean? If we have a voltage source and we have several branches of resistance, we can find IT, the total current, by finding I1, I2, I3, and adding them together. We did not need to do the total resistance. Now if we add a resistor here in the main line to, if there is resistance in the main line, we must find RT to find IT, which this example we just did was like that, because it basically had two resistors in here. We couldn't find separate branch currents and sum them together to get IT, because we can't find the branch currents, because these resistors cause the voltage to be different across the branches than was supplied by the supply. Without those resistors, the supply voltage applies to each branch, which makes it very easy to calculate the current in that branch. But when you add the resistors, now you have to calculate RT in order to get IT and work your way through like with using that like we just did. Now, once we find RT, and we did this in our last example, the source voltage is applied to RT, which allows us to find IT. And what we did in that last example, which you do with this one, we reduced this whole network to a single resistor. Then we had a voltage source, we had a total resistance of RT, and from that we were able to calculate IT, which was, I'm going to call it voltage total, voltage applied, whatever. IT was equal to VT over RT. So when we have a circuit with resistances in series, before you get to the parallel branches, you have to reduce it to the equivalent resistance, which we just did in the example we just worked on. And the fourth thing that we want to talk about, these are kind of rules related to analyzing series circuits. Any series R has its own IR drop or voltage drop, which must be less than the voltage applied. Also, IT, each branch current must be less than IT. And I think that's probably starting to make sense to you now. The one we just did, we reduced it to 3 different resistors. We had 200 volts supplied, and we used the IR drops and found that we had 60 volts, 20 volts, and 120 volts. Let's look at that first part here. Each series has its own IR, must be less than VA. And you'll see each of these voltages, 120 is less than 200, 20 is less than 200, 60 is less than 200. We cannot have voltage drops that are greater than the applied voltage. In the circuit we just drew, we had a voltage source. I think we had 2 amps out of it, and it split into 1 amp and 1 amp, and then it split even further into half amp. Basically, each branch current must be less than IT. IT we found to be 2 amps. That branch was 1 amp. That was less than 2 amps. That branch was 1 amp. That was less than 2 amps. And for this section, it's not IT, but it is the supply to that section. We had 1 amp there, half amp here, half amp there. They were both less than 1 amp. So those are kind of your basic ideas, and we've been going over them to analyzing series and parallel combination circuits. And we're going to work on a few of them. Say we have a circuit, we'll draw you another circuit, and we have a couple of resistors, one resistor here, we have another two resistors in series here. $120 volts here. We have R1, which we're going to call 40 ohms. We have R2, which we're going to call 50 ohms. And R3, which is 10 ohms. We'd like to find, we want to find IT, we want to find I'm going to call it IA, I want to find IB, so let's start by finding those currents. We want to analyze this circuit. Let's see. We can find IA pretty easily because we have 40 ohms, 120 volts. So we'll use that I equals V over R. And we have here 120 volts. IA will equal 120 volts, which we have supplied from the supply across both of these branches, 120 volts, and we have 40 ohms. So what's 120 by 40? That's 3 amps. So we have 3 amps here in this branch. Now to find this branch, we need to use the total current. And we can see that the total current, R2 plus R3 is 50 plus 10, that's 60. So we have 60 ohms in this branch. So let's find IB. IB is equal to the same 120 volts supplied. And we found that we had 50 plus 10, 60 ohms. So we have 120 divided by 60. We have 2 amps. So we have 2 amps here. Now remember that each of the branch circuits is going to be less than the total IT. So we know that the IT is going to be more than 3, as we know it's going to be more than 2. Well, it turns out it's the sum of the two. We actually have 3 amps here. 3 amps equals IT. So we have 3 amps being supplied by the circuit, and we have 3 amps going through R1 for current B, or current A. We have 3 amps, 2 amps going through the series combination of R2 and R3 for what we call current B. So we found all the currents. So if we want to find voltages, well, this voltage is given. Let's try to find our voltage across R2 and our voltage across R3. Now we have a formula that we've used quite a bit. Voltage equals I times R. Hence the term IR drop, voltage drop. So R2, we're going to call this voltage 2, which is voltage across R2, is equal to the current through R2, which we found to be 2 amps, times the resistance of R2, which we found to be 50 ohms, 2 times 50, 100 volts. So let's write right here, V2 equals 100 volts. Let's try to find the voltage across R3. We'll call the voltage across R3 to be V3. V3 equals, same 2 amps. Current in a series circuit is the same everywhere. And this is a series section over here. So we've got the same 2 amps. We've got 10 ohms. Well, 2 times 10 gives us 20 volts. So V3 equals 20 volts. And you will notice that 20 volts plus 100 volts gives the 120 supplied. The 120 volts supplied causes 3 amps here and 2 amps here. And this illustrates that first rule that we had talked about. Basically said that rule number 1, I'm just going to put a big star here. If there are parallel strings across a main line, we do not need our total, or we sometimes call our equivalent, to find IT. And you notice we did not find RT. Now, if we had wanted to find RT, we would have combined these 50 and 10 to make 60. We'd have calculated the parallel combination of 60 and 40. We'd have found something less than the smallest resistor, something less than 40. And then we could divide 120 by that to get the current. We didn't do that. We didn't have to do that because the voltage is supplied directly to each branch. The main line being this line that goes here supplies the voltage. This line that goes here supplies the voltage. Let's just do one more little quick thing here. We have our formula we see many times. Form of Ohm's law says resistance equals voltage divided by current. We've also used that to say that RT equals VT, or V applied, divided by IT. Well, we have VT, which is 120 volts. We have IT, which is 3 amps. Let's do that calculation and see what we get. 120 volts divided by okay, I've made this is 5 amps here. Excuse me. Combine these. That's 5 amps. Yeah, that's why it doesn't look right. $5 Now we see that IT is greater than both of the branch currents, and that IT is also the sum of the 2 branch currents. So 120 volts divided by 5 amps. That's what we wanted to get. 120 divided by 5. That should be 24 ohms. Let's check that with the calculator real quickly. Yes, 24 ohms. So we got 24 ohms for RT equals 24 ohms. And that is in fact less than the 40 ohms. That is in fact less than the combination of 50 and 10, which was 60, as we expected it to be. So I think that's all. I think that's all we're going to do today. We got a lot of circuits to analyze. It's going to take some time, but we've pretty well demonstrated that first point. If there are parallel strings across the main line, we do not need RT to find IT. And we never found RT until the end. We did it kind of as an academic exercise. Anyway, thanks for coming back, and be sure to like and subscribe. And until the next time, keep on learning.